Happy Friday, guys, if this gets out today. This game dev update video is going to be a little bit different from previous ones because I've recorded a bunch of my progress or my process in making progress in what I have to show today. But just as a preview, I have this truck here. I think it was in my previous video as a static object, and today it is now a fully drivable vehicle full of rangers here. So I think if you want to see how this came into being, then you might enjoy getting a little glimpse of my process in making this working, semi-working truck in the Quake engine, just using entirely Quake script, Quake C. And yeah, I mean, it's not flawless by any means. There's plenty of room for improvement, but I thought this would be a good point to do a bit of an update, because as you can see, it moves in 3D space in all directions, and it's able to rotate on all axes and cover all sorts of janky terrain that should have never been made using trench broom. And it does an okay job of covering that kind of terrain. But yeah, I can accelerate and then I can slow down. I have a sort of an orbital camera, and got a driver, a passenger, a guy in the back who shoots lasers because they look cooler than other projectiles. Yeah, and so I'm going to try and polish this up a bit and get it back into probably a more vanilla build of Quake. That way I can play some of the vanilla Quake levels and just sort of showcase what I've made here. So that's basically what you're going to see if you watch any more of this video. Enjoy. My objective here is to get this truck into Quake, a game and a game engine that has no support for vehicles and only very basic physics and collision. So it's going to take a bit of work to get this in. My goals with the truck, physics-wise, are that it steers like a normal truck, can drive around, steers from the front, and not pivoting on its center point, and has some very basic suspension physics as well. So I have a bunch of code here that's completely untested and uncompiled. Never tried to compile it yet. It's basically pseudocode in that case, but I'm going to try and walk through everything that's going on here just to get our basic truck physics going. So I have this, you could almost call it a free body diagram. It just says essentially what our goals here are. So I have this dotted line, so we want our truck to drive in a logical way. So it steers with the front tires, it's not a prelude or something, and it drives in this arc, but the exact arc that the front wheels take and the rear wheels take can be slightly different due to various factors, from the geometry to forces acting on the vehicle. So I have some vectors drawn out, vertical, horizontal, the forwards and the lateral, up and down. Doesn't follow the right-hand rule or anything, but I think we'll survive. And then our different rotational axes, so roll, pitch, and yaw. And my goal here with all this code that I've written out is to determine what all these vectors need to be represented as in the code. So we're primarily going to be working with velocities here, because I want all the motions to be interpolated, and this engine at its lowest levels has no conception of force or energy. So the only effective way I have that's representing what's going on physics-wise is by using the velocity fields and the angular velocity fields of this vehicle, and deriving all the physics interactions from that. And it's all going to be approximations and not exact calculations of what I want. But just starting, I have my animation frames defined. Those will eventually come into play, but I start by defining vectors 1, 2, 3, and 4. They don't get immediately used, but in this case, vectors 1, 2, 3, and 4 correspond to 4 virtual wheel entities. So I'll sort of represent these in the drawing. So these, in this particular case of the way I have it modeled right now, the truck, so everything here purple, and the wheels, it's all one model, with animations to show steering and suspension deflections, I guess. And so these 4 vectors are connected to these 4 virtual wheel entities. They have no model, but they do participate in the game physics. So these have the step move type, which means that every tenth of a second, they move a discrete distance. So 0.1 seconds, they move a discrete distance, say 4 units. And within that tenth of a second's time period, the game engine, modern source ports of Quake, will interpolate that motion. So if you're, say, 0.05 seconds after this step has been called, then it will display the truck 2 units forward, and then that full tenth of a second later, from the start, it will be 4 units forward of where it was. So I have 4 different vectors for the 4 different virtual wheels. And right now I'm just taking a placeholder distance instead of taking a throttle input from the keyboard. That will be one of the next things I need to add. But I am taking a input, a direction using the mouse aim. So the perspective of the driver, if it were first person, it would be aiming like that, say. Or if I'm doing third person, then there'll be a camera up here, and the mouse aim will go somewhere like there, and there'll be a forwards and a right component to that aim, and the vertical components of where you're aiming will be ignored, because I'm really just interested in the yaw of the aim. so this angle here, that's what the front tires are going to be doing. Then I also normalize that, convert it to a yaw that we can use for math. And so once I have all the inputs, what I do now is I look at the work that the front wheels are doing against the momentum of the vehicle. So at this point in the code, the front wheels all move in an ideal way using the engine's walk move, so that discrete movement type. So front left and the front right wheels, they move their discrete distance at their angle. And the physics engine comes into play where it will determine, are these wheels actually on the ground or are you flying through the air? That's one check it does. And if the wheels, when they attempt to move their specific number of units in their yaw direction, if that ends up somewhere in a wall or off the ground, then the physics engine will account for that. So if it can't move forward, then it'll stop. And if the wheels would go off the ground, then that's corrected and they fall down. Or if they come into a small ledge that the vehicle would be able to drive over, then they stair step up. They move upwards. They move upwards a discrete amount, say up 18 units. That's the maximum distance in Quake that an entity can typically stair step up, and it's a decent amount of distance, but I'll probably leave it. And so we need all this information to determine how the front of the vehicle would ideally want to move before taking into account the forces working against that motion. So what I have here is it's not quite a loop, but a repeating set of instructions. So the engine determines that the self entity, so the entity in focus, becomes one of the wheels. Actually, it becomes one of the virtual wheels. And that virtual wheel, it moves its discrete amount, and the physics engine determines how that should behave. But before it can actually make that motion, there's a couple of things that need to be figured out. So the first is, where should this virtual wheel be before it moves? Because that's not actually a trivial piece of information. We need to make sure that this wheel, this virtual wheel, starts in the correct offset from the center of the vehicle's body, because in the previous calculation, this wheel will have been moved to its ideal location based off the user's inputs, but the actual game physics and the actual physical interactions that I've coded here are going to determine where the actual truck ends up and its angles and velocities. So this virtual wheel can become disconnected from where it needs to actually be. So in order to determine that, we call make vectors on truck.angles. So that essentially gives us our forwards, so our V forwards, and our V right, and I believe it's V up. Angles, or not angles, are vectors from the angles of the truck. And by multiplying these forwards, up, and right vectors by the forwards, up, and right offsets of the wheels, then you can get the translated offset of the wheels in 3D space based off of the translation of the vehicle, particularly the angles. And so we can reset the origin of each virtual wheel. From there, we call the walk move, and the walk move function, engine function, takes two variable, or takes two pieces of information in, has two inputs. The yaw for the motion, and the distance that it moves. So the yaw that the front wheels want to be going is that inputs, which is which should be clamped to perpendicular to the vehicle, because you can't turn your front wheels all the way around the back of the car. So I have a basic calculation for that. It's not here, but I won't worry about that. So after that direction has been clamped, so each of the wheels move in their ideal direction and distance based off of throttle and steering inputs. We then determine if the physics has caused this to not move where we ideally asked it to move. So if there was an obstruction, or the wheel moved up or down due to stepping up or gravity, then we determine that difference between where we expected to go and where we actually went. And when we take that distance, we can then multiply that distance by some number less than 1. And when we do that, the purpose would be to simulate the damping of the vehicle's suspension. So if we have a spring and damper combination on this wheel, you can, or I've chosen to simplify that interaction as being a deflection ratio. So if I wanted the movement of the truck to be 60% the movements of the wheel in any given discrete time period, but I multiply that by 0.6, and to get from the measured deflection to a velocity, I multiply that by 10, which is the same as dividing by 1/10 of a second. And I do the same thing for both front wheels before approaching the rear wheels. Let me cut the recording there. All right, so I had a change on my desktop that I hadn't pushed to the origin, but essentially all that was that clamping of the steering yaw to being forwards of the vehicle. So let's go back to the rear wheels. So the first thing that I calculate with the rear wheels is the axle yaw. So we can figure that out. The new axle yaw I should specify after the wheels, the virtual wheels have moved. That new lateral axle yaw can be just determined by taking the difference from one origin to the other, and then that can be converted into a yaw using the vect2 yaw function. So once I have that, I can also get the original yaw of the truck by calling vector yaw on the angles of the truck. And I can find another vector that I need, which I've called the pivots. First, I find the essentially this point here, the center point of the front of the vehicle. So the center of the front axle. If we drew that axle, then that's that center point. It's just the average of the two wheels points, and then that pivots vector is the vector from that point to the center of the truck. And what I do with all of this is scroll down a little bit, get a bit more information, but this is a lot of this. I get the vector, yep. So we can now set our self entity to one of the rear virtual wheels and do the same thing we did with the front wheels, where we are setting the origin to be where would ideally be after the transforms of the vehicle. And we call our walk move, but we aren't calling our walk move in the direction that the player is aiming. We're setting our walk move in the direction that the chassis of the car is pointing. So ideally, the rear wheels want to go the direction that the rear wheels are pointing, which is the direction that the vehicle was already facing. And of course, we also calculate our damped vertical velocity impulse to the chassis from each of these wheels. Once we have all of the velocity represented impulses to the chassis from all four wheels after making their ideal movements, what I'm going to do now is determine the motions along each of these vectors of the chassis itself. So I do some basic sums of what would be forces, but in this case, they're estimated forces from these velocities. So the first one that I do is I sum all of the lift on the vehicle. So the vertical components from each of the four virtual wheels gets added together along with the velocity that the chassis of the truck is already on. And that gets our sum of the vertical components. I then calculate the roll and the pitch. So the roll and the pitch, and that is all based off of, first I calculate the roll from the vertical components of each wheel multiplied by their offset in the y direction. And then the other components that goes into the roll is the y components of their movement multiplied by their vertical offset. So when you're taking a sum of the essentially the moments around this vehicle, so like this, there's two ways you do that. You either take this right offset, so along this direction, if we have a vertical impulse along these offsets, think of it like a bar, it turns the vehicle like this. And then you can achieve the same thing if you have a vertical offset. Let's not draw that. If you have that vertical offset, then it creates the same effect, the same spinning effect. So we do that in both the roll direction and the pitch direction, but the yaw of the vehicle is handled differently. The yaw is the most complicated element of the steering because that's what the steering is really focused on, and that's the part that I want to get right. So the first thing I do when calculating the yaw effect is determine which vehicles were actually on the ground, and that's calculated for us using this on-ground flag. And if the on-ground flag comes back false, then that means that I'm not going to consider any force coming from the in horizontal plane motions of the ideal wheels, because they're not on the ground. They aren't exerting any sort of force or doing any sort of work on the chassis. So we negate those if that case comes into effect. And then the next thing we do is we clamp the amount of work done by each of these wheels by essentially the amount of grip that they have. So I am representing grip by a constant of friction multiplied by the vertical component of the impulse, which is a stand-in for the normal force. So if you don't know how grip works or how friction works, essentially, if you have this force pushing down, so that's the weight, that's the weight of our body, then the amount of friction there is resisting motion is equal to the coefficient of friction times the normal force. Have a normal force plus the weight, they sum to 0. So when a item is in its equilibrium state, so it's not accelerating up or down, then that always equals 0. That's what that means. And so we can determine that to see how much of that ideal work can actually be done when we take into account how much grip each tire has. Let's see. And so this final sum in this part of the code, it just sums the essentially the momentum or more closely the kinetic energy of this vehicle that it already had with the work that each of the 4 tires are trying to do once you account for the grip. And so the front tires, that work that it's trying to do is the difference between the velocity that it wants to have and the velocity that it already has in the horizontal plane, whereas the work that the rear tires are trying to do is just the amount of grip that it has in the direction that the vehicle is moving. And we determine, we limit this grip, or the work done by each tire, to the grip by looking at the horizontal vectors, so these 2-dimensional vectors of the grip that it has, so the maximum potential work versus the work that it's trying to do. And it's just a comparison of vector lengths using the VLEN function. And from there, we have our SVEC. So that is the chassis velocity, and the AVEC, which is the chassis angular velocity. The SVEC can now be made into the existing SVEC, the existing chassis velocity plus all of that, the effect of all the work. And the A velocity of the actual truck entity can also be set. So we've calculated the effect of each four-wheel. We sum it up to, in our moment calculations or our rotational calculations, and in our clamped work calculations, we have all of that information, we sum it up, and we apply it to the actual vehicle entity, and that is the end of one physics frame. And so I'm going to test all of that and find out just how wrong it is. All right, I'm back on my desktop the next day, and this is going to be my blind reaction to all of this code I just got to compile, not doing what I expected it to do at all. Get you out of the way. Compile the map. Well, that's a start. See if there's anything there at all. No, there ain't nothing. All right, so I changed the prog stat, and I changed the move type to none just to make sure that there wasn't some physics issue causing it to despawn. But yeah, now it's in the game. And if I show the bounding box, it looks about right. Can I stand on it? Might be too high. Oh yeah. It's definitely a truck. Right now I'm enabling the wheels, so let's see what happens there. Do I have any more entities? I don't see them. All right, so I got the, well, I got something to show up. I think it's the wheels. I was doing something wrong with setting the origin. It looks like I'm still doing something wrong with setting the origin. But I've realized I have a bit of a concern here. If I want the player to collide with the truck, then I need the truck to block physics objects. And if I want the wheels to be able to walk along the ground and interact with physics objects, then it also has to be a type of solid that interacts with physics objects. So I'm not sure how I'm going to deal with needing both the actual model of the truck and the virtual wheels to both interact with physics objects in certain ways, but I don't want them interacting with one another. All right, so the bigger problem with my code was that I just had the my while loop set up wrong. I was adding to my counting integer before actually entering the looping function that I wanted to do. So now I have that set up. I have my four wheels appearing in the four places, and they're all connected to this truck vehicle. So I guess next I should turn on or change their physics type to ones that actually have movement, change their movement type and their physics type, and see if this just falls through the ground or something. All right, now this whole thing, all 5 entities are solid slide boxes. The wheels have move type step, and I gave the actual model move type bounce to see what would happen, and nothing's happening, so I guess that's better than something catastrophic happening. I'm not sure. But now I need to get the actual, I guess, physics that I coded to actually do something and not just rely on the game physics to, I guess, do nothing at this point. All right, it's time to test my physics loop with placeholder inputs of straightforwards and no throttle. So let's see what we have here. The wheels have now popped out from under the car. It's kind of bizarre. Kind of stuck. Yeah, that's not. This is suboptimal. All right, so I've discovered one thing that was going wrong. So this wheel here is, and these wheels are the front wheels. These wheels are the back wheels. So the wheels of the car right now are perpendicular to the car. I turned the collision off on all these parts. So they weren't getting pushed out from under. They're actually rotated 90 degrees from where they should be. And it looks like the combination of solid trigger and move type toss should be usable for just testing the physics loop. Then I can determine how to get collision with players later. All right, I've turned all of my offsets 90 degrees, so this should just work now. And I'm saying that with a hint of irony. It's not going to just work, but it might be closer. All right. We now have wheels and sort of where they need to be. Going to need to correct those offsets a little bit eventually, but yeah, we have a car. Should probably right away for the player to take control so that I can test how it behaves while driving. So now I've written this overly simple function to pilot the truck. I guess we can see what it actually does. Give that a quick compile. And copy. Paste and save. And run. Let's see. Press C to drive truck. Oh dear. Well then. That's really something. All right, I'm going to test now with just moving the car and hopefully different results. Maybe. Doesn't seem to be doing anything now. I am the driver of the car. Boxes, one. The wheels are in place. The car is there. Doesn't seem to be moving. Let's figure that out. Well, I think this is worth showing off. You could call it progress of some sort. Oh, let's try that again. There we go. Yeah, the truck's definitely doing something now. All right, now let's see what happens when I give it a moment to settle before activating the physics. Oh. If I made the sky brighter, be able to tell better what's going on. But yeah, it's flying. Oh, is it falling now? No, I think it's just stuck up there. Well, that's suboptimal. Can I see it up there? No, it's gone now. All right, now let's try with a reduced vertical component. Well, the vertical component was definitely reduced. All right, now I'm going to test it with 1/10 the angular velocity. Well, that's not quite right. Okay, now the truck should theoretically have no angular velocity at the end of each physics frame. Right. All right. If I look over here, does it go over here? No. All right. All right, now it's going to go 10 times slower. So you can really see what's going on. Okay, so aiming seems to have some effect on where it goes. Maybe. Maybe it's just random. I'm looking over here, it's going over there. And I'm looking over here, it's still going over there. Does it ever change direction? Yeah. Now it's going right, and I'm looking to its left. It's going left, and I'm looking to its right. Okay, that's progress. That's something. So now the truck should be doing the opposite of what it was doing before. Should be doing the opposite of what it was doing before. No, not that. All right. I multiplied the aiming direction by -1, thinking that it would mirror the direction it is trying to move the truck, but clearly it didn't do that. Okay, so what's really weird to me is that the truck it goes in somewhat the opposite direction I'm looking if I'm standing behind the truck, right? But if I stand to the side of the truck, it just always goes this diagonal forwards and left. I stand on this side of the truck, it goes, I guess it's going forwards and right. But it goes forwards and left if I'm looking to the left. Okay. I'm standing in front of the truck. It always goes forwards and left. So that's interesting. So when I stand to the right of the truck, it's sort of doing the right thing. Sort of. Okay, it looks like with a little bit of intelligent debugging, I've gotten the angles for steering right. So now if I look to the truck's right, moves right, tries to go right, move to the truck's, if I aim to the truck's left, it tries to go left. And then I think turning around is a little less perfect looking, but it still understands that it wants to go left or right. Now I gotta get actually steering to work. Because yeah, we can't have this vehicle slowly sliding side to side. I have reintroduced yaw to the equation, so let's see what happens. That's not yaw. Just going to confirm that y and not z is in fact yaw. Yeah. It looks like yaw. We can even sort of drive around. Hey. Look at that. It's sort of controllable almost. Let me finish fixing the code because it's getting its yaw, its angular velocity from what I thought was going to be, I think, pitch. Time to see if I finally have my vectors right. We're looking a little slippery here. Yeah, this isn't quite what I was hoping for. If we hit that, are we going to stop? Wow. Yeah, I'm gonna need to think about this a little more. So it is morning of day 3. Last yesterday afternoon, I was looking at the bounding boxes for the rear wheels of the truck and where they were appearing. And I noticed that they were way too far behind the vehicle. And so I thought about why that might be. And I was looking at the vectors for the rear wheels and remembered that there was a part in the code that I couldn't really follow. And that's because I had skipped a step when calculating those vectors. So if we have our layouts for our car, for our truck, we have these wheels. And I'm relatively confident that I was able to determine where the front wheels should go. So they have this angle that they want to travel. And so we can measure that relative to straightforwards. But it's less clear where the rear wheels should go. But what I know is that the truck is relatively rigid, which means, so we calculated the pivot point here because this distance from the wheel to the center of the front of the vehicle, that never changes. The wheel doesn't move relative to the car, it's a solid object. And then I also calculated the distance from this pivot point to the center point of the vehicle. That doesn't move either. Now, to find where these rear tires go, should also consider this distance never changes, this distance never changes, and this distance never changes, which means that this distance never changes, and this distance never changes. Now, when the front wheels move, they end up here and here, and there's a new pivot point here that follows that same trajectory as the wheels themselves. So we know that we want this distance here to be equal to the distance from the new center of the vehicle to here. So the new center should be somewhere around here. And we know that this diagonal line here should be the same length, whether it's here or here. But we don't know the angle. Let's see. So what do? We determine the new angle from here to here. And if we know that angle, then we can add that angle to this angle and get our new location for these wheels. So That's more that. So end up with something like that. I haven't gone through these notes this morning yet, so I'm trying to remember how I calculated this angle here. But I think, yeah, I think it's just, so we have our forward angle here that we were originally going, and then our new vector from the original center point to the new pivot point. We take that angle and we can modify the vector from our old rear wheel position to our new center of mass. Not mass, because this car has no mass, but the origin point of the vehicle. So if I use that vector calculation instead of what the math in the code right now is doing, is trying to apply this angle directly in place of this angle. And so that angle is obviously wrong, which would explain why the car is constantly trying to spin. And somewhat explains a possible reason that the wheels are too far backwards would just be that I threw in this distance here, and it's now trying to move the wheels that distance in the wrong way. And I could flip that around, but it's still going to be wrong. I need to calculate the actual distance that these wheels need to travel and at what angle they need to be traveling. And I suppose it's time to reveal the effect of using new vectors. Yeah, sure. All right. All right, I forgot to save progs.dat, so maybe I'll do something better. Oh. Wow. All right. All right, well, I flipped a dot product around and everything appears to be in the right place now. The truck slid sideways a little bit and then stopped moving, so I'm not sure exactly what happened. And it also has an obscene velocity that's probably even higher now. Yep. So yeah, I guess I'll figure out what is up with that. So I think this is notable progress, so I'm going to show what's going on now. Look at that. The truck is actually moving in a semi-controlled manner. I can steer it. It's always moving forwards because I have no throttle input. It's steering the wrong way again, which is something I had fixed before. Last time I was able to get it to hit this elite. Yeah, there we go. I mean, it's basically perfect if I can actually run over a monster. And then it falls. But yeah, I just obviously the yaw calculation isn't quite right because it's not actually turning. There is a yaw angular velocity being calculated, but it doesn't seem to be doing much. But the vehicle is steerable and it's moving, and it's moving in a controlled manner, so I think that's a huge development. So what have I done? So I realized after last time I shared what was going on that I cannot rely on the game's physics engine to handle anything to do with gravity. Even though I set all the wheels to use a move type that is affected by gravity, I would think that using that move type would mean that if the wheels were on the ground, then the game would set the flag for being on the ground. If the wheels weren't on the ground, the game would clear that flag. And if the wheels weren't on the ground, then they would fall and there would be some sort of downwards velocity, but I could not rely on that. So instead, see, where am I? At the beginning of each, the logic for each wheel, I have this check where if there's no vertical velocity, I'm just going to assume that we're on the ground because it is doing that right. Like I'm not, the wheels aren't falling through the ground. So I'm just setting that flag manually, adding the on the ground flag. And then obviously gravity, if I'm handling that myself, gravity needs to be factored in whether the vehicle is actually moving down or not. So I'm adding, subtracting 10 to the vertical velocity every physics frame, regardless as to if the wheels are, like you saw at the ends where the vehicle drove off the edge and it was falling. There's obviously a vertical velocity happening there, but we need a vertical velocity happening always in order for the grip calculation to do anything whatsoever. And then to counteract that, I have at the end here that if the truck is moving down, so it's falling, but the truck detects that it's on the ground, which it does do for some reason more correctly than the wheels do, then I'm neutralizing that vertical velocity there, so it's not actually going to fall through the ground. And then I'm just getting rid of that on the ground flag because for some reason having that on the ground flag was causing it to get stuck, even though it's move type fly, it doesn't interact with the ground. It was getting stuck anyways. And then I was also setting the vertical velocity components of, I guess what's being added, so this vertical velocity component here to 0, so that's the amount of vertical velocity, yeah, that's is being carried as momentum. I might change this line though, just because the vehicle at this point isn't actually accelerating when it's in free fall. And then let's see, other change I made. So the way that I was calculating the angular velocity from the yaw was fundamentally backwards before, where I was essentially calculating a moment when I needed an angular velocity. The difference between a moment and the angular velocity is that the moment has essentially two factors of distance. So the units for a moment would be like force times a like a radius distance, and so you would get the distance being factored in there twice when multiplying in that what I was calling work multiplied by the offset. But what I actually want is an angular velocity in radians that's a unitless measurement over time. And so to get that, I have to divide by the offset, not multiply by the offset. So I changed that. And then I also changed the vectors of, I may have already covered this, but the vectors for the rear wheels, what they're acting along. And then I also changed how grip works when the vehicle is trying to move faster than it should be able to move. So if a vehicle is driving along the road, whether it's in a straight line or at an angle, it's not going to just keep picking up speed forever and ever. Eventually you get to the point where your wheels are turning as fast as they're going to turn your driving flat out. And if you keep the engine at the same RPMs and you stay in the same gear, your car is not going to continually get faster and faster. So I'm solving for that, essentially what needs to be subtracted from the calculation by taking the vector of essentially the vehicle's momentum and subtracting the vector of where the actual work that the truck can do would take you. Let me scroll down to where that's actually happening. So it's over here. So I'm taking that trajectory of grip minus the velocity. So grip working against momentum, taking just the direction, that's what it means to normalize it, and then multiplying it by the length of the grip. So I'm only walking back the velocity of the vehicle by the amount of grip. So essentially, imagine you have a car that's sort of going so fast around a corner that it's beginning to slide. Well, the amount of grip that the tires do have in that slide would be counteracting its essentially over velocity over what it's able to actively do. So now I need to figure out essentially my angular velocities are still a little bit out of control. Right now I'm just completely excluding pitch and roll because if you saw in the debug prints, those numbers were completely out of control, and then I need to figure out why the yaw that's being calculated, the angular velocity in the yaw is reasonable, but the vehicle isn't actually turning. So I need to figure out why that is. Just walking the dog. Just walking the dog. Made some progress. Unfortunately, this is mostly a hack, but it's working a lot better than it was. Could probably make it around the track that I built here, but it would take a while. And the movement is really janky, and the steering doesn't take account for grip or momentum at all. But I'm sure I can fix all of that. All right, so I turned momentum back on it. It doesn't seem to have done anything, at least nothing detrimental. So I've been testing what would happen if I try to drive through this big concrete wall. And there's something going on. I mean, I can't just drive right through the concrete wall, which is a bonus. Seems like the bounding box has some effect, some exaggerated effect on this side, whereas if I go onto this side of the wall, I can drive almost all the way inside of the concrete wall for some reason. And I don't have the faintest idea why that would be true. Might be stuck for real now. Well, I guess I'm redoing this because OBS appears to have crashed. But hopefully for real this time, this is the last time I'm standing in front of this whiteboard for this project, or for this part of the project. So what I wanted to cover here was, up until now, when trying to calculate the pitch and the roll of the vehicle, what I've been doing is I took the movements of these four wheels, these 3D distances, these deltas, and I tried to convert them into an angular velocity by multiplying by the reciprocal of time, and then converting from a velocity to angular velocity components to add up to sum into a total for the vehicle. And that math is really hard for me to follow, to really understand in my mind that this is doing the correct behavior. And just from what I can see, testing the code, it's not doing what I expect. And so I decided to make a change of plans to something similar to the way that I hacked the yaw of the vehicle to work, where I had already calculated to get these differences, these distance impulses. I had calculated an ideal chassis yaw vector, not a yaw, but an ideal chassis vector, as opposed to the steering vector, which is adapted from the input's direction vector. So I have this chassis vector, and it's influenced by all the things that would ideally be influencing the pitch, the roll, and the yaw of the truck. And as I try to implement more physics interactions, then I can also add the effects of those interactions in as distance impulses to that vector, which is a much simpler way of understanding the result of the physics interactions on the vehicle. And so what I can do now is I can convert that vector, which is derived from essentially the starting locations of all four wheels and their offsets, their delta offsets. So if it moved up, so then that delta there, if it moves forward, delta in that direction. So these 3D space differences from where they started, just adding all that together and essentially taking this average. So we're dividing by 2 because if we take the position of our front two wheels divided by 2, that gives us our average position for one end of the vector. And if we take the positions of these two wheels, divide that by 2, we get the other end of this vector. And so we subtract one end from the other end, then we get the whole length of this vector in 3D space. We can convert that to angles using vector angles. And then if we take the difference between these new desired angles and the angles that we already have, we multiply that difference by 10, which is the reciprocal of the time, which is a tenth of a second between frames. Then we get the 3D vector of angular velocities that the vehicle needs to be on to smoothly transition from its current angles to our desired angles at the end of the frame. And so that's what I'm going to be implementing now. So with that change, we finally have our ideal pitches and our ideal yaws working. Obviously, there's still a long ways to go. All right, it is 9 o'clock at night on Tuesday. And everything is technically working. It's just a little bit jank, but it steers. It can go up slopes. It can go down slopes. It's affected by gravity. So I think that's pretty good. Just had to lock in for a couple days. I'm sure I can smooth that out somehow. All right, I want to see if I can make it look like this is working perfectly on the first take. Well, that was a little iffy, but look at how smooth this is moving. All right. We're not crabbing too hard. It could be improved a little bit, but we're turning. It follows my cursor. It's moving buttery smooth. Look at that. We can go up this incline. We can go down. And we're having a bit of a pitch issue. See if we can do that again. But look at how it goes down the first time. Look at that. It pitches down buttery smooth. You can do the stairs too. We made it. We didn't flip into the ground, so I'm going to take that as a win. Look at that. Now the suspension is a little weird. Because right now it's being modeled as if the suspension can extend infinitely when the car is above the ground, so I just need to fix that. But we are so close. All right, check it out. This is actually a lot better than I thought this would get today. Look at that. Third person camera. It feels way more natural than I would think. It still has some trouble, but I can drive over these stairs, drive on this uneven surface, and look at that roll. Look at that. I even have the wheels in front if you see. They are in fact steering. I guess what I have to do next is obviously I'm only going at one speed, so I need to figure out how I'm going to deal with that. Either getting some sort of input through WASD for controlling velocity, or trying to use some other keys to use set speeds, because I tried to implement getting out of the car, and last I checked, it doesn't do anything when I press E, which was the impulse to get in and out of the vehicle. So I'm going to need to figure out if I want to be able to change the velocity of the vehicle. Then I need to figure out how to do button inputs while I'm in here. Oh, okay, jumping was a bad choice. Guys, I've come really far with this truck in the last 2 weeks, compared to where it was just, I would walk up to it, press E, and it would just flip out, fly to the other side of the world. And all the physics, all the assumptions were basically wrong, and I had to redo it all. This truck, I can get in. I haven't figured out how to get back out yet. For some reason, it's not taking my impulses, but I learned from yesterday when I went to test for driving, and I pressed the space bar and saw that jumping was interfering with my camera control, that I do have access to the space bar. I do have access to the jump button, so I made that into the throttle, and look at that. I even put this awful, almost intraversable mountain on this level. You can see there's definitely room for improvement in the physics, but the fact that I can just drive on this at all in Quake, in the Quake engine, using Iron Whale right now, that's crazy to me. Look at that. Just driving on over it. And so I have steering working even when I'm not moving forwards. It's based on where I'm aiming. I can give it throttle. I can let off the throttle. And then if I'm not on a glitchy spot, it just slowly comes to a stop. I guess there is no such thing as not a glitchy spot, but if I'm lucky, it'll just slow down in a way that makes sense. But yeah. It's got pitch, roll and yaw. Moves in 3D space. Can climb these hills. I think it'll be really fun to throw a little AI ranger in the back and have him shooting at enemies and try to complete some vanilla Quake levels. This might be too big. I might have to make it a mini truck. We'll see how that goes. Well, yeah, it goes in reverse. It's not the most typical driving in reverse controls, but I kind of like it. So, even though the collision with or vertical surfaces isn't great, I can still get out. It's pretty cool. Not sure what I would want to implement next. One idea I had was that I could do a trace line, a ray cast, to check for these solid walls because that's not the greatest collision right there. If I did a traceline raycast, I'd probably do a better job. But then I'm not sure what I can do about the truck not wanting to get close to this side, to this face of the wall. But yeah, guess I'll just have to think about what else I can add right now. Maybe the gunner, maybe I'll try doing some AI trucks, see how those function. That was almost cool. This is pretty fun. I'm not even doing anything. I want this guy to shoot on his own, but this is cool too. So I figured I would end this by giving some highlights of the code. Just starting with the spawn functions and then going through some of the physics, mostly the things that I had to change at some point, things that in the beginning of when I was developing this truck, I thought, I theorized that I could do it one way, but I ended up having to change things. And starting the spawn function, I'm not sure I actually had to change this, but I did experiment with different settings and ended up, for the truck's body, I'm using the solid trigger setting along with the move type of fly. And what that results to is that the solid trigger, it actually does have some level of collision, but it's not as strict as say, what is it, solid slide box that you would normally use for monsters. Then the move type fly is because, again, it has that, I guess, more liberal application than trying to use move type step. It's always discrete, so it's controlled using velocity instead of a series of steps. So that ended up working well for the body of the truck. Move type fly also allows you to have a angular velocity in the roll direction. One thing I had to mess with is the bounding box size, particularly the bottom. The truck wouldn't be able to go over small obstacles if the bottom of the bounding box was level with the bottom of the wheels. So by raising that up, it became possible for these virtual wheel entities to move step up onto a higher elevation without the bounding box of this solid trigger volume getting caught on the edges of whatever I was trying to drive over. And then I have some spawn functions associated with the truck for the wheels and the ranger dudes in the truck. Those are all spawned separately. The wheels are they're spawned at various offsets. These have the move type step, like I said. They're also trigger volume solids. Then I'll go up to, so truck drive, that's my function. Just sort of the main function called by the truck every tenth of a second. So this is technically an animation function. So yeah, it calls itself at the end of every animation frame. It just checks, it calls the pilot and physics functions, which I'll explain, and then it does some logic to determine what animation frame. Right now I only have 2 frames for the wheels turning, so they sort of jitter back and forth, but you rarely ever see the wheels while you're moving. It's really hard to see. And then I have these functions, copy walk, which I have on the left side of my screen. And that essentially does a bunch of math, like way too much math, to determine where all the child entities of this truck need to be, what their velocities need to be so that it looks like they're smoothly attached to the body of the truck. They don't follow it perfectly one-to-one, but they just they stay on in a very natural way. I wouldn't want to use this function for something that's supposed to be rigidly attached, but when it's people in the truck, it looks completely natural. Yeah, so that's copying, or it's finding essentially the velocity that any item on the vehicle needs to have the velocity and angular velocity, so that's at the end of the next animation frame, they've reached essentially the end of the difference between where they are and where they're supposed to be. And then the velocity and angular velocity of the vehicle that they're parented to is taken into account. So they theoretically shouldn't have that difference between where they are and where they're supposed to be to cover in the first place. They theoretically should be following the transforms of the parent object in discrete time, but there's always going to be that little difference because it's only taking that sample every tenth of a second, and it can't take account for things like physics collisions or stepping up. Anyways, I guess I'll go to truck pilots. So that is called, or it's called here in the animation function, but the player becomes a pilot of the truck when he goes up to the truck and presses impulse 16, which is a custom binding. I'll have to change that if I make it a standalone mod. Essentially, once you've called truck touch, then the player is the pilot, or the truck dot driver. And so all these things are set, and the real important part of this function is that the player is sort of just transformed into a camera. So you get rid of your weapon model, the player becomes move type fly, and we take this aim function and essentially invert that. So whatever direction you're looking, the player now orbits in that opposite direction with an offset of 60. And so you're 60 units above the truck, flying 200 units behind the truck and facing the direction that you're aiming. So you're always looking towards the truck. Then I have a dismount function as well, but it doesn't work. I don't know why. But now to the actual physics. So we got that aiming done in truck pilots, and that direction that you're aiming gets passed into drive and then as steer, and then passed into the physics. So here's the new physics function. It starts here. So let's see, where do I start? There's a bunch of things, but essentially we start a bunch of vectors. So the truck's current velocity, the truck's current angular velocity, and then this vector tvec or temp vec. And that is just a tenth of a quarter of the vehicle's velocity. So essentially the distance that the truck moves every frame. So that's why it's a 1/10, is because the truck will move a tenth of its velocity in a frame, and then the quarter is because this is divided by 4 because of the 4 wheels. And so that comes into play a few times. We have this fake dist. Essentially, if you're not giving any throttle to the vehicle, then it takes that temporary vector and divides its length by 4 again, which sort of smooths out the deceleration of the vehicle when you let off the throttle. So the way that the truck figures out where to go is it calls a walk move on the each wheel. So the front wheels go in a steer direction, a steer yaw, and the rear wheels go in a chassis yaw. And essentially there's a bunch of math here to figure out where the wheels start from and where they're going to get that steer yaw in the front. And then in the back, we calculate this point's pivots, which is the average point between the front wheels. And we offset that by the z and find the vector from that center point between the front wheels after they've moved and the center point of the vehicle, and that becomes a direction that's the rest of the vehicle is moving. See, there's one more thing I wanted to point out, which is, let's see. So we have our vec2 or vec1. Vec1 and 2 are the essentially the contributions to the physics from the front wheels. So we see vec1 becomes, let's ignore this for a little bit. That's an edge case. So vec1 becomes the difference between where the front wheels are after physics and where they should theoretically start the frame based on the translations of the vehicle model. And so vec1 in the x and y directions is determined after the walk move has been called, but in the z direction, it's actually calculated at the beginning of the physics pre-think, essentially before the walk move is actually called. And that's because the effects of gravity on move type step objects is discrete. So especially since I have a vertical velocity aspect to these wheels. So essentially between these frames every tenth of a second, the wheels are falling in real time. And so to capture that distance, we need to essentially capture that distance. And after that, we can call our new walk move for the frame to capture the horizontal movements of the wheels after the throttle input and the steering input. It's similar idea for the rear wheels. The vertical distance is captured first, then the origin is reset. Front and rear wheels origin is reset before calling that walk move. And then for the X and Y delta, it's based off of that walk move, whereas the vertical delta is based on before the walk move due to gravity. And then I have this function here, z control, which I haven't explained yet. So that's also on the left side. That's essentially my simplified damping function. So there's a bunch of comparisons here that, to put it simply, there's a maximum deflection in which I want to account for the effect of damping. So think of it as your vehicle's suspension. To a certain point, it compresses, but after that, it's fully compressed, and so it can't absorb any more deflection. So I have this this variable c, which is my damping ratio, and essentially, since I defined damping as 0.6, that means that 6/10 of the deflection that was calculated for that frame within the range of the suspension will be accounted for, and the other 4/10 won't be passed on to the chassis of the vehicle immediately. And that's all this really does. Then I go into grip. So I tried a few different ways to calculate grip. This seems like the most reasonable approximation that I've done. So I have my floats, F grip, forward grip, essentially trying to take into consideration the fact that the wheels are turning in a certain direction, so there can be a lot more movement in that direction versus the R grip, the right grip. So essentially the lateral movement of the wheels, that's calculated using a different factor. And then S grip is stands for sliding grip, essentially a secondary factor once the movement of the wheels has reached the limit of the grip. I still have another factor there to continue to smooth out the motion. And so the forward grip is proportional to the throttle input because it's obviously the forward movement of the vehicle is proportional to the throttle input. So you could almost think of, if I remove the throttle inputs, so you're moving faster than you have forward grip, that's less to do with the tires trying to stop you because you're braking, and more you could think of it as like engine braking. And so I have some math to determine the impacts of forward and lateral grip on each of, I guess, the vectors, the contributions from each wheel. And then because I was really hoping that I would be able to rely on the game's physics to say, hey, these are move type step entities. So could you determine for me, are you falling right now? Like, are you in the air? Is the on-ground flag true or false? Like, I thought I'd be able to rely on that in the beginning, but it turns out that that's a completely unreliable flag for at least my application. I don't know why it was so unreliable for me, but I was able to approximate that, well, if the vehicle is falling and vec1.z isn't just the velocity of the wheel. If I go back up, uh, see vec4.z, right, it's that damped effect. So, so if that is not just below 0, but below -1, because I have this added 1 here, but if it's below -1, then I know that there's no way that there's any grip contribution from this wheel. Otherwise, the grip contribution is 1 plus that, or 1 subtract that vertical components multiplied by that grip factor. And the 1 is there because essentially there's always that influence of gravity on the vehicle, on the wheels, whether or not it's actually moving down, right? Because if the vehicle is sitting on level ground, it's not the velocity, there's no downwards component to the velocity, but it is still accelerating down. There's just no effect of that in the physics engine. There's no measurement of that downwards velocity due to gravity because the vehicle is in static equilibrium in the vertical direction. So I just account for that by adding this 1 here. And the grip is used to turn these vec 1, 2, 3, and 4 contributions into work. So I have this local vector work. It's only working, or it's only following this calculation in the xy plane, so there's no z component to it. And I use this function I wrote, it's called xy limit. So the work is equal to the xy limits, limiting the work to the grip, and then multiplying that by throttle, which is not a it's not an integer or a floating point number for how much throttle you're giving, but rather it's determining the direction in the xy plane that you're going. So I showed that before, where if you stop giving it throttle, then instead of the wheels working to push you forwards, there's sort of that simulated engine braking to slow you down. And so xy limit has more steps than I thought it would originally, but that's because the limits given, and so I should explain the variables. So there's given and there's limit. Given would be the work, so the contribution you're starting with, and then limit is the grip, because the contribution of work is limited by the amount of grip you have available. And so essentially I break these both into their x and y components, and then you can actually have my grip vector could be pointing in the wrong direction for my work vector, but you know that shouldn't really change the behavior of the work being limited by the grip, because grip doesn't have a direction. It just has a value. So that's how that function works. And then after limiting the work by the grip, I create a new vector called control. The reason that I have it separated into work and control is because work is going to influence the direction in angles, in terms of angles that the vehicle moves, whereas the control, which becomes this control calculated here plus the influence of work. That is the vector that actually controls the direction that the vehicle's chassis moves in 3D space. So that control vector is obtained through the function xy control, which takes in the work, the t-vex, so that's a tenth of a quarter of the velocities of the vehicle, and then the sliding grip factor. And so this is how the control function works. Essentially, it finds the difference between the work that the wheels are contributing, and essentially like what the vehicle would be doing if it had no momentum, if it had no pre-existing velocities, and it compares that to the existing velocity of the vehicle. And if the pre-existing velocity is on a different vector from the work, or if it is greater in magnitude than the work of essentially the influence of that work limited to the grip is it takes it and has it work against that component of the velocity that is exceeding what the work would be doing in that direction. And then with the remainder, it multiplies it by that sliding grip factor, and essentially removes part of the remainder as well. And that just, the effect is that it controls the vehicle so it doesn't accelerate indefinitely in any direction. And so this is where sort of everything comes together. Oh yeah, I should say, I also multiply the z by throttle because I've multiplied everything else by throttle, and so I can multiply it by throttle again, the whole vectors, instead of breaking it down into components later on. But that's just a convenience thing. So the actual travel, that is the vehicle's existing velocity is equal, or the vehicle's velocity is equal to its velocity plus the influence of all these control vectors multiplied by 10, because at this point they're still in terms of deflections. And then we create these vectors, final vector and final angs. And essentially the final vector is the goal vector of the vehicle at the end of this frame. So it just adds the influence of the work. The first two are positive, the second two are negative. So front positive, rear negative, plus this forward vector, which is the sort of a normalized vector of where the vehicle is pointing, multiplied by the throttle direction, and then converted to angles, because working with vectors was, well, it's a little unintuitive, but also it's to get the correct angular velocity. Just the best way to do that is to convert this vector into angles. So we have essentially a list of the angles in 3D space that we want this vehicle to be pointing. So the first angle I calculate is the pitch. Just taking the difference between that ideal end of frame pitch and the current pitch of the vehicle. I use this function a lot, just correcting the angular differences, so that if you turn from 350 degrees to 10 degrees, it doesn't make you do a full turnaround. It knows that you just turn those 20 degrees in the other direction. And those angular velocities are turned into the difference between the angles. Just multiplied by 1 here, because then I can fine-tune things. And then I do the same thing with, or a similar thing with yaw. Um, just find the difference here, and then I convert that yaw, or I convert that angle, um, I convert that vector, I should say, into a yaw, which is different from a difference of angles dot y in some specific ways that come into play later. And then I do something sort of interesting is that I redefine the final vector as being, I believe it's right minus, or it's left minus right. And then I take those, I should say it's left minus right plus the existing direction to the right, so 90 degrees from this forward vector. And I convert that to angles, and then I treat the pitch of that angle as the roll of the truck, because this vector angles function can't produce a roll. So I do that. And then I find the starting yaw. And so this is where I actually apply. So the truck's angular velocity becomes a vec. The truck's regular velocity becomes s vec. I have this fix for when the truck gets stuck in the ground. Just moves it up by the distance from the bottom of the bounding box to where the bottom of the bounding box should be when it isn't stuck in the ground. And it does that fix whenever the bounding box returns that it is on the ground, which it does actually do when it's stuck, thankfully. But it doesn't just do that. It does it when it also it multiplies the velocity of the truck in the vertical direction by that 0.025, and it adds it to the height of the truck in the previous frame. And if the truck hasn't moved, then it knows that it's stuck. Because if you have a velocity trying to push you up because you're stuck in the ground, and then the next frame you haven't gone up, then that's how it knows that the truck is stuck. And then I set the truck ideal yaw. This is necessary to use the change yaw function, which you need to use for the angles of the bounding box to actually change, and for all the essentially for the physics to work. You need to use change yaw and not just set an angular velocity. And then finally for the animations, I need a direction, whether I'm turning left or right or going straight. And so that's calculated here in this function, just because I have so many vectors already going on. And that's everything going into the physics of this truck that allows it to move around in 3D space. The camera is still very shaky, and I'm not sure what I'm going to do to fix that, but I definitely want to fix that. But yeah, it allows it to step up over items. If I show the bounding boxes, you can see where the wheels are, those wheel entities. The bounding box doesn't appear to turn, but from a physics perspective and from a math perspective, the truck is actually turning. The only exception to sort of the physics behaving in a way that makes sense based off of the transforms of the truck is that on this face of this concrete barrier, the truck can essentially stick itself halfway in, whereas on the opposite face, really, on this opposite face of the barrier of a truck, can't go any closer than the bounding box. So that's that one exception that I'm not sure why it works in one way but not the other. But I'm thinking of adding a trace line, essentially casting out a ray from the origin of the truck to the edge of where its bounding box should be if it was following the transforms properly, to determine if the truck can move forwards or not, just so that you can't drive halfway into a wall. But I'm not sure how I would get around the truck refusing to enter uh, essentially a certain distance from the other side of the wall. Maybe I'll just make the bounding box of the truck smaller once I have that replacement for the wall collision. But yeah, that's all I have to share this week.